Today we're going to be talking about a pre-calculus technique that is designed to get you ready for something you will need to know in calculus called resolving a rational expression into partial fractions. The idea here is thinking about the fact, and don't write this down, I'm just going to write this over to the side. If I took something like 1/3 plus 7/6 and I wanted to add those together, actually I'm going to use a slightly different example, 1/3 plus 2/5. I would need to find a common denominator. I would need to multiply this one by 5/5 and this one by 3/3, and I would end up with 5/15 plus 6/15 is 11/15. Now the idea here is if I wanted to go backwards, if I wanted to take this 11/15 and split it up into two fractions, I know that I could look at the factors of 15, 3 times 5, and I could probably come up with fractions that had those different denominators, but then I would have to figure out what numerators I would need in order to add them together and get 11 in the numerator. So this is the idea of what we're going to do with this rational expression. We are going to take the rational expression and factor the denominator into two linear factors, x plus 5 and x minus 3. And I can rewrite this rational expression as the sum of two simpler rational expressions with x plus 5 and x minus 3 in the denominator. The numerators are unknown, so I'm just going to call them a and b. Now think about what I would have to do to multiply or to add these two fractions together to get back to the original rational expression. I would have to multiply the first term by x minus 3 over x minus 3, and I would have to multiply the second term by x plus 5 over x plus 5. So in the numerator I would have ax minus 3a plus bx plus 5b all over x plus 5 times x minus 3. And of course that's equal to 12x plus 4 all over x plus 5 x minus 3. So notice the denominators are the same. I already know my denominators are the same, so that means if these two expressions are equal to each other, the numerators must also be the same. Specifically, ax plus bx has to equal 12x, and negative 3a plus 5b has to equal 4. So I'm going to write a system of equations. Ax plus bx equals 12x, which means a plus b have to equal 12, and negative 3a plus 5b have to equal 4. Well, to solve a system of equations, one method I can do is just to take this whole equation and multiply it by 3 and write it over here. So this would be 3a plus 3b is equal to 36. Adding these together, I get 8b is equal to 40, or b is equal to 5. So I know what b is. If I take b equal to 5 and put it back into this equation, it's very obvious then that a is equal to 7. So the answer here is 7 over x plus 5 plus 5 over x minus 3. And these add together to give me the 12x plus 4 over x squared plus 2x minus 15. Now I can check this by just going back through the process that I used. 7 over x plus 5 times x minus 3 over x minus 3 plus 5 over x minus 3 times x plus 5 over x plus 5 should give me my original problem. So this would be 7x minus 21 plus 5x plus 25 all over my original denominator. And you can see from the numerator that I have 12x plus 4 in my numerator, and those would multiply together in the denominator to give me x squared plus 2x minus 15. So I'm good. Now I would like you to try one of these problems. So we go to the next page. Oh, it's at the bottom of this page. Oh no, actually before you try this problem, I wanted to show you something graphically first. So notice here is the graph, the rational expression function graph of the original problem, 12x plus 4 over x squared plus 2x minus 15. Since the denominator factors to x plus 5, x minus 3, and there are no common factors in the numerator, I have two vertical asymptotes at -5 and at 3. Since the denominator has a higher degree than the numerator, I have a vertical or a horizontal asymptote at 0 as x goes to infinity. If I were to graph each one of these separately, notice this has the vertical asymptote at -5, and this one has a vertical asymptote at 3. If I graph these two together on the same screen, it would look something like this. And notice this graph just takes that middle part and combines it into one smooth curve, and it still has the two sides look the same as these two individual graphs. So it's kind of an interesting graphical analysis of what we just did. Now what I'd like you to do is to take the same method and try this one. Pause the video right now and work the problem, see if you can get the answer right, and then turn it back on and I'll reveal the answer. Okay, now that you have turned this back on, let's reveal here. All right, so you can see, extend this page up a little bit so it's easier to see. Here would be the technique. Here are my two factors. And I think I don't know if I factored the numerator or denominator up ahead, but this would be the technique. Actually, just check your answer right now rather than me babbling on. And if for some reason it's not correct, take a look at your work, check it, see what you did wrong, see if you have any questions to ask. And I'm going to move on to the next example. Okay, now we're going to learn a shortcut for doing the same thing. It's called the cover-up method because you use your finger literally to cover up one of the factors. So if I want to find a, for example, a has a denominator of x plus 5. So I go back to my original function with the factored denominator and I cover up the x plus 5 and I substitute -5 into the rest of the expression. So for a, I let x equal -5. Notice that is the 0 of the denominator. I cover up that factor and then I substitute -5 everywhere else. So the numerator is -60 plus 4 over -8, -56 over -8, which is 7. So a equals 7. B, now we cover up the factor that is under the b. That's supposed to be a finger with a red fingernail, by the way, if you're wondering what this odd-looking thing is. All my students tell me it creeps them out. I'm going to let x equal 3, and now I'm going to put 3 into the rest of the expression. So now I have 3 plus 5 in the denominator, so this is 36 plus 4 over 8, which is 40 over 8, which is 5. So notice that is a very much simpler way to do this. I want you to be able to do both methods, however. Now try the cover-up method with the second one. This is the same example you did before, and you already know what the answer is supposed to be. So try the cover-up method with this one, and pause if you need to, and then I will reveal the answer. Okay, now you're back. I will reveal the answer. This is how you would set up your work. Here would be your A and your B, the way those are worked out. So check your work, make sure you understand this method. And then we're going to go on to the next example. Now this one is, try this problem. Notice you have the graph of the denominator. Notice this is just the graph of the denominator. So I'm going to write this down. This is necessary so that you can factor the denominator. You need to know what the zeros of the denominator are. So you see 3 zeros right here. So you can write the factors that go with each of those zeros to factor the denominator. And then you can use, I would suggest using the cover-up method to find A, B, and C. So if you understand what to do, pause it and try it. If not, you can listen to me work through the problem and pause it at any time to try to complete the problem yourself. Okay, so if you've decided not to pause and you want to listen, or if you're checking your work, here goes. The first factor, this is -5, -2, and +3 are my zeros. So my factors are x plus 5, x plus 2, and x minus 3. So I can set this up as equal to a over x plus 5 plus b over x plus 2 plus c over x minus 3. And then I'm going to use the cover-up method here. A then, and I have this little movable x here. I'm going to cover up the x plus 5, substitute x equals negative 5 into the rest of the expression. So I have negative 5 squared minus 20 times negative 5 minus 29 all over negative 5 plus 2 times negative 5 minus 3. And then this turns out to equal 96 over 24, which turns out to be 4. So A equals 4. Anytime if you want to pause and figure out the rest of them, you can. You can actually see at the bottom, my answer is not quite covered up down here, but I'll go through and set up the next two. For B now, oops, I don't move that, I move this. So I cover up the x plus 2, and it really is good to actually literally cover it up with your finger. It helps. And I'm substituting x equals negative 2 into everything else. So negative 2 squared minus 20 times negative 2 minus 29 all over negative 2 plus 5 and negative 2 minus 3. That turns out to be 15 over negative 15. So my B is 1. And actually you can kind of ignore this because I have it set up differently down here. And then my C is plugging x equals 3 into everything. So I have 3 squared minus 20 times 3 minus 29 all over 3. Oops, I forgot to move my x. Move this. Come on. Ah, everything's moving but my x. This is not good. Come on, little x. All right, never mind. I'm just going to move it. I'm just going to put an x right here. I'll try to get rid of this one. Boy, I can't get anything to move. There we go. Get rid of that. And then I can say this is going to be 3 plus 5 times 3 plus 2. Obviously, if I had put it in the wrong factor, I would have gotten 0 in the denominator, which wouldn't have worked, and I think I would have recognized the problem. This turns out to be negative 80 over 40, which is negative 2. So C is equal to negative 2. So I would write that as 4 over x plus 5 plus 1, actually negative 1, sorry, negative 1 over x plus 2 plus negative 2 over x minus 3. Okay, so that would be 1. You would obviously need a little help factoring the denominator. You would have at least need to have known 1, 0, and you could use synthetic division and quadratic formula to find the other two. But for the purposes of these problems, I'll give you enough information so that the factoring is not the issue. Just want to know that you can split it up or resolve it into partial fractions. Now this last slide is an explanation of why the cover-up method works. And I'm just going to let you kind of look at this right here. I'll talk about it just a brief bit here, and you can look at it in the printed notes online if you need to kind of convince yourself that this does work. But if I were trying to solve for A, for example, it would be helpful to multiply both sides of the equation by x minus 3 so that I would eliminate the denominator and get A by itself. So when I multiply both sides by x minus 3, notice that the x minus 3 divides out here and here, and it also divides out here and here. So I would have 2x plus 1 over x plus 2 on the left-hand side. The denominator, then I would have an x minus 3 in the numerator next to the b over x plus 2. And then if I solve for A, then I would have 2x plus 1 over x plus 2 minus b times x minus 3 over x plus 2. Now notice in the cover-up method, what I do is I substitute 3 in for x. Now notice if I substitute 3 in for x here, the numerator would become 0 here. And so this whole term wouldn't make any difference at all. It would be irrelevant. And so what it ends up being is that I'm substituting 3 into 2x plus 1 over x plus 2, which is exactly what I would do if I covered up the x minus 3. So the value of A depends only on the 2x plus 1 over the x plus 2. And I could show that the same thing is true for the B term. I could do the same thing. So that's why the cover-up method works. It's not just a trick, it's a trick based on an algebraic technique. And any little tricks you ever learn in algebra are based on an algebraic technique. Okay, so hopefully that was enough of information so that you can do partial fractions problems on your own now.